In chapter 2 here, we're going to start looking at this idea of proving things and using different types of reasoning and logic to develop arguments that just follow a logical sequence that are based on facts and that just make sense. Okay, and so the first thing we're going to look at is this idea of using inductive reasoning. Okay, and so that's the idea, is that by the end of the lesson, by the end of this video, you understand what inductive reasoning is and how to use it in geometry. So what is inductive reasoning? It's the process of finding a pattern for specific cases and then writing a conjecture for the general case. Okay, so you look at a couple of instances and then you just kind of lump that into one big idea and write a conjecture, which just is well, you can see right next, okay, is a statement that is based on observations. Okay, so, hey, this is what I think is true because this is what I've seen. All right, these are the facts that I know. These are the patterns I've observed. And so now I'm going to take that and write a general statement. Okay, so to show that a conjecture is true, you must show that it is true for all cases. Okay, and if you want to show it's false, you must find a counterexample, one specific counterexample for which the conjecture is false. Okay, so for a conjecture to be true, it's got to work all the time, 100%, no doubt about it. Okay, for it to be false, just find one case where it doesn't work out, and that thing is false. So I know your papers were not shaded. So if I look at this, okay, and it says describe how to sketch the fourth figure in the pattern and then sketch the fourth figure. Okay, well, if I look at this, okay, so this guy's got 1, 2, and the bottom one shaded. This one's got 1, 2, 3, 4, bottom left is shaded. 1, 2, 3, 4, 5, 6, bottom left is shaded. So you'll notice each time I go, I'm adding 2 additional boxes. So my description would be 8 boxes. I don't want to write that out. Work smarter, not harder, right? So 8 boxes, and the bottom left will be shaded. Okay, so 8 boxes. There's 8 boxes. The bottom left guy is shaded. That is inductive reasoning. I recognize the pattern from figure 1 to figure 2, from figure 2 to figure 3, and then I can go ahead and continue that pattern based on those observations. All right, example 2 says describe the pattern in the numbers. Okay, so now we're talking numeric patterns. Okay, we have -1, -4, -16, -64. Okay. Write the next 3 numbers in the pattern. Well, here's the pattern I notice. Okay, this is the opposite of 1 squared. This is the opposite of 2 squared. This is the opposite of 4 squared. And the next one's the opposite of 8 squared. Okay, so the description I'm going to make is that it's the opposite of the square of 2 times the previous. Okay, you can describe it however you want. That's just what I came up with. Okay, so the first one is the opposite of 1 squared, then you have the opposite of 2 squared, the opposite of 4 squared, the opposite of 8 squared. Okay, and so then what I'm going to say is I'm thinking that the next pattern is going to be the opposite of 16 squared, the opposite of 32 squared, and whoops, the squared should be inside, and then the opposite of 64 squared. Okay, and obviously I'm not going to leave my answers like that. I'm going to actually plug them in. So 16 squared is one that you probably should know. That's 256. So I have -256. 32 squared, don't expect you to know. So that's -1024. And 64 squared is -4096. Okay, so I observed a pattern, I applied that pattern, and that's what I've used to create the next 3 numbers in the sequence. Okay, all right, I'm going to go ahead and scoot this guy up a little bit. Part B says describe the pattern in the numbers 1, 2.5, 4, 5.5, and write the next three numbers in the pattern. Okay, well, let's see here. To go from here to here, add 1.5. To go from here to here, add 1.5. Add 1.5. Okay, some patterns are easier to see than others. Maybe if you were to pause the video and try to identify the pattern, you may not have seen that right away. Okay, but I did. So the description is add 1.5 to previous. Okay, so clearly 5.5 plus 1.5 is 7. 7 plus 1.5 is 8.5. 8.5 plus 1.5 is 10. All right, so, and again, the more that you look at this, you know, sometimes the easier these patterns are going to be for you to see. I'm going to skip this one. I took this one out of your notes. Example number 4 on mine, 3 on yours says numbers such as 3, 4, and 5 are called consecutive numbers. Make and test a conjecture about the sum of any 3 consecutive numbers. Okay, so well, let's see here. 3 plus 4 plus 5, that's 12. Let's just take any other random ones. Let's just take, oh, I don't know. Let's take 7 plus 8 plus 9, that's 24. Let's see here. 22 plus 23 plus 24 is, let's see here, 20, 40, 60, 65, 60, 69, 20, 40, 60, 69, 73. Am I going crazy? I am crazy, aren't I? 22, 23, that's 45, plus 24 is 69. Well, that just threw me for a loop, because I was initially going to make the argument that the sum of any 3 consecutive numbers will always have to be an even number. Okay, so that's not going to work out. Let's see here. Oh, this is kind of an odd one. I don't know that any of you would have noticed this, but if I do 4 times 3, that's 12. 8 times 3 is 24, and 23 times 3 is 69. I'm going to grab a couple more just to see if that actually makes sense. So let's just take smaller ones, make our life easier. 11, 12, and 13. Let's see, that's 25, 35, 36. 12 times 3 is 36. All right, so maybe I did find a pattern. Okay, conjecture. The sum of any 3 consecutive numbers will be 3 times the middle number. Okay, so what I'm saying, my conjecture is that you take and you add any 3 numbers in a row. The pattern will be that the sum will be 3 times the middle number. Okay, and that's all you had to do there, was write a conjecture. Okay, in part B it says numbers such as 1, 3, and 5 are called consecutive odd integers. Okay, or odd numbers. Make and test a conjecture about the sum of any 3 consecutive odd numbers. So I have 1, 3, and 5, that's 9. Let's see here, I have 3, 5, and 7, that's 15. I have 5, 7, and 9, that's 21. Okay, so if you notice, it appears as though that pattern is remaining the same. Okay, let's just try a couple more consecutive odd integers. 21, 23, 25. Let's see here, that's what, 44, 64, 69. 23 times 3 is 69. That's okay. One more, 15, 17, and 19. That adds up to 42, 51. And 3 times 17 is 51. I think we got it. Okay, so the conjecture, the sum of any 3 consecutive odd integers will be 3 times the middle number. Okay, So that's what we're looking at there. Just looking for patterns, testing. You know, here I tested 1, 2, 3, 4, 5. Sometimes you may need to test more than that to see the pattern. Maybe you never see the pattern. Okay, it's just you just got to keep working through them and keep looking every different angle you can. Okay, it says make and test a conjecture about the sign of the product of any three negative numbers. This one should be pretty easy for you, right? It doesn't matter if I take any three negative numbers, -2, -4, -22. What can you tell me immediately about that product? Hopefully you're sitting over there on the other side of this computer saying, I can multiply those and I know for a fact my answer is going to be negative. So the conjecture, the product of any three negative numbers will always be negative. Okay? Again, those are just my... When you're taking notes, I'm telling you, you're going to want to get to a point where you're taking efficient notes, okay, and using symbols to represent things, just so that, you know, when you're trying to catch up with a professor down the road, you know, they're not going to slow down for you. You're going to have to kind of pick up your pace. So that's just a little mathematical tip there as you're progressing here. So example 6 says, a student makes the following conjecture about the difference of two numbers. Find a counterexample to disprove the student's conjecture. So again, I'm looking for one specific case. It says the difference of any two numbers is always smaller than the larger number. Okay. Well, if my numbers are positive, 4 minus 2 equals 2, okay, this number is smaller than 4. However, if I go ahead and dive into negative numbers, or even use 0, okay, if I say, let's see here, if I go 0 minus 2, 0 minus 2, that's -2. Okay, that's -2. I suppose that's still smaller than the bigger number, right? That's still smaller than 2. Okay, but now what if I take that 2 and I make it negative? So what if I say 0 minus -2? Well, now that's going to be plus plus. That's +2. Okay, this number 2 was bigger than both of these that I started with. I started with 0 and -2. Okay, so there is my counterexample. No, wait a second. 0 minus -2 is +2, and +2, all right, is bigger than both of them. Is bigger than the 2, or I should say is bigger than the 0, because 0 was the bigger number to start, right? 0 is bigger than -2. So that's this idea of this counterexample. Okay, find one specific example. Okay, find a counterexample to disprove the following conjecture. Supplementary angles are always adjacent. No, they're not. Those two angles are supplementary, but they're not adjacent. They add up to 180, right? But they are not adjacent. There is your counterexample. It's one specific case where this conjecture does not hold true. Okay, so again, the idea from today is that you are confident in understanding what a conjecture is, using inductive reasoning to find patterns, and the next few items in that sequence, and then obviously, like we just talked about, finding counterexamples.